Hello everyone, myself Mohd Shaikh Sabir. I am a master student from IIT Kanpur, and in today's talk, I'm going to talk on the topic of spin wave interference device for low power physical neuromorphic hardware. Okay, so the general motivation is we have CMOS system, okay, which is the fundamental for all of electronic systems, which is our day-to-day life. But then we have Moore's law, which says that the number of transistors on microchips doubles every 2 years. But recently we came to know that it is actually not doubling, it is actually saturating. So the point is, as more and more transistors we are going to pack within a particular area, the resistance is nothing but rho L by A. So area is decreasing, the resistance increases. So we will have joule heating, and also there will be a lot of quantum properties that will affect the devices. So for that, we need to go beyond CMOS technology and find some other paradigms through which we can do computing. Okay. So for that, we have spintronics. So what is spintronics? It is a paradigm for electronics wherein we use the magnetic moment or the spin property of the electron and use its functionality. Okay. So in general, first we have charge current, where there is the flow of charges, the electrons, but there is no net flow of spins. There are equal number of plus half and minus half spins. But then in spintronics, we have spin polarized current, wherein if you pass a charge current through a ferromagnetic material which has a magnetization, then the polarization of the spin, which matches with the magnetization of the material, dominates. So there is a single polarization which dominates. So we have this spin polarization current. Then finally, we have this interesting pure spin current, where there is no net flow of charges, but then we have net flow of spins in a particular direction. So the charge current is zero, but there is spin current. So one can imagine if we can do functionalities using only spin current, then we can have joule-less heating devices. How we can generate this pure spin current? Okay, the method is actually spin Hall effect. So what is spin Hall effect? We have a heavy metal which is a high spin orbit coupling. So heavy metal means this atomic number is very high. So if you pass a charge current through a heavy metal, so due to the spin orbit coupling, the HSOC for the opposite polarized spins will have be opposite sign due to the L dot S. This S is plus half for plus half spin and minus half for the negative spin. So they will actually segregate, and we have a spin current injection in the perpendicular direction. So if we have an adjacent ferromagnetic material, we can use this injected spin current to apply a torque on the magnetization of the material, because the spin current is nothing but the angular momentum. So this flow of angular momentum in the adjacent ferromagnetic material, we have a torque on the magnetization of the material, which can actually precise about its effective magnetic field. And the dynamics of this magnetization in the ferromagnetic material is given by this LLGS equation, Landau, Lifshitz, Gilberts, and Strolinski equation. So the last term, the term marked in red, is actually the term corresponding to the spin current contribution. Okay. Using this spin current injection, we can generate spin waves. So I'll come to the topic, what are spin waves? Okay. So spin waves are nothing but magnetic excitations in the ordering of a magnetic material. So suppose in a ferromagnetic material, we have all the spins aligned in a similar manner. So the net angle between both the spin is zero. So the next possible excited state is when a single spin flips in the opposite direction. But we know this is not possible because all other spins will try to pull the single spin towards them in the direction. So a cheaper alternative in terms of energy is that the single spin reversal is actually shared by all the other spins. Then the resultant what we get is nothing but a magnon, a quasi-particle of spin wave. Okay, and these spin wave are mainly dominated by these two interactions. The first is the exchange interaction, which is actually short range. By short range, I mean the wavelength is small. Okay, so if the wavelength is small, then the angle between the neighboring spin moments is large. So the exchange interaction is large. So it dominates. Whereas in the long range, long wavelength, between every maxima and every minima, all the spins, the angle between them is small. So they collectively act as a single dipole. So the dipole interaction dominates. These can give some interesting features in the dispersion relation. Okay. Now, coming to my main research work, this is a proposed device. Okay. This is a completely simulation-based work. So in the light blue, we have an ferromagnetic material, yttrium and garnet, which is a medium for propagating spin waves. And the dark blue is the platinum, which is nothing but a heavy metal, which has high spin orbit coupling. So the device is in this manner. So at the left and the right boundary, we have this platinum interface with IIG, and we have these two notches. We apply this charge current pulses from both the ends, left as well as the right. So the charge current pulse basically pass through the PT. Due to the spin-Hall effect, we have the spin current injection into the adjacent Voyage layer, we can see here. So the magnetization in the Voyage layer precesses. This precession, this non-local injection of the spin current actually generates propagating spin waves towards these notches. And these spin waves pass through the notches towards the region of interest, and eventually they'll interfere and we'll get some interference pattern. So this is the main idea. So here you can see for single current pulse, this is the spin-Hall oscillator. By spin-Hall oscillator, I mean the interface at both the boundaries, the PT-YG interface. This is the spin-Hall oscillator dynamics. For single current pulse, we can see as long as the current pulse is activated, we can see the dynamics actually, the amplitude increases, and as this pulse is switched off, it actually gradually decays. Okay. Yeah. So here you can see the spin wave spatiotemporal data. We have a single current pulse, and here you can see from 1 nanosecond to 12 nanosecond, we have this excitation, propagation, and eventually the decay of spin waves. One interesting important point to note here is that the memory of this current pulse is carried by the spin wave for a time duration of 12 nanosecond. So we have a 12 nanosecond of domain within which we can do some computations and use this spin wave for computing. Okay. So here we define two states, the on-off state and the on-on state. By on-off, I mean only the one PT-YG interface oscillator is switched on. That means the current pulse is sent only on the left side, whereas the on-on state, we send the current pulse on both the sides. Okay. So here we can clearly see when we have current pulse on both the sides, the spin wave from both the notches pass through them, and eventually they will interfere at the region of interest. And if we calculate the spatial intensity, we get some this maxima and minimas. Okay, so if for experimental purposes, we can apply an interface, a platinum interface at the region of interest as well. And using the inverse spin-Hall effect, we can calculate the voltage across this platinum and actually measure the dynamics, the dynamical of the spin wave. So here I have plotted this average of the region of interest. And as usual, one can see that due to the on-on state, the intensity is high compared to the on-off state. Now coming to the computing part, how can we use this for computing? Okay, so basically we will use this device for this 4-bit classification. 4-bit, we mean that the 10101000. So total there are 16 bits. Okay, what we'll do, we'll give these bits as input current pulses in our device, and we'll measure the interference patterns. Okay, for experimental purposes, we can actually detect the voltage, but for understanding, I have shown here the spatiotemporal data. Okay, so the important point to note is that, as we have seen in the previous slide, a single current pulse has a fading memory up to 12 nanosecond. So any current pulse that comes before 12 nanosecond will affect the dynamics. So this 1001 and 0101 will have different interference patterns. So from this, we can classify all the 16-bit pulses. And how can we quantify this interference pattern? Okay, as said, for experimental purpose, we can simply take the average. But here, for simplicity, we have taken the maximum of the amplitude. So in that manner, we get all the current pulses and the corresponding amplitude. So from this, we can clearly see that we are able to classify this 4-bit pulses. Okay. And one thing is how this 4-bit pulse, this amplitude variation is at a particular time. How can we know that after applying the 4-bit pulses, at what time should we measure the intensity? So for that, we developed an index, the separability index, which is nothing, shows the separability of all these current pulses between themselves. Okay. So here we get after 12 nanosecond, when all the four current pulses are switched off, we get a maximum at the separability index and then gradually decay due to the spin wave damping. So at this point, approximately around 30 nanosecond, we get the separability index maximum. So if we experimentally measure the intensity at this point, then we can use it for computing purposes efficiently. So finally, we use our device to make a spin wave network model. Okay. So from this, we actually showed the classification of this MNIST handwritten digit dataset. So there are 60,000 0 to 9 digits, training digits, as well as 10,000 test digits. So what we'll do, we have an input digit, we'll convert this into a binarized form. So wherever we have a threshold, wherever the pixel is below the threshold, it will be converted to black. Wherever it is above the threshold, it will be converted to white. And we have a 2D matrix. It will be swept across this image. And wherever there is a white pixel, it means there will be current pulse 1. Wherever there is a black pixel, there will be current pulse 0. So from this, we have this 28 cross 28 image. From this, we get an 196 cross 1 array of input current pulses. We will give this current pulse into our device and get the corresponding spin wave output. And
so you have 1 more minute.
Okay. This output will send in the classifier layer and for further classification. Our results show that there is actually, we can see that we have this spin wave device. So there is no need for additional layers. We need only the classifier layer. So there is a reduction of approximately around 98% in the weight parameters. There is some reduction in the accuracy as well, but the weight parameters in reduction gives a significant motivation that we can continue this work further. Yeah, I'd like to acknowledge my supervisors and co-supervisor, Professor Rohit Madam and Yasir Fukma. Thank you, everyone.
Very nice presentation, Sabir. So now the floor is open for questions.
Hi,
Yeah.
Sabir.
Hello.
Can you hear? Very nice presentation. Maybe I missed something, but can you briefly tell me what is that region of interest between your YAG slab and why it is 200 nanometer? What is the rationale behind choosing that 200 nanometer area? And what is this ROI actually?
Okay.
Yeah.
ROI is for the simulation purpose is just a region where we will measure this interference and all. Okay, this 400 nanometer you're talking about, right?
Yeah.
Okay, there is no physical significance. It is just a parameter that we set so that we get some amount of wavelengths so that we can get some interference. Okay, so it should not be small enough that it doesn't cover the wavelength itself. So to get the pattern, we need some amount of length such that we get the interference pattern. So yeah.
Okay, so you are saying in just simulation, you just choose this area to measure your spin wave dynamics in that particular area, right?
Yeah, exactly.
Thank you.
Experimentally, we can simply put a platinum on this region of interest and get the dynamics corresponding to that.
Thank you, Sabir. Thank you.
Okay, one more question you can take. Okay. So if there is no questions, then thank you so much, Sabir, for your nice